In the last episode, we were talking about the normalized Laplacian, and I wanted to talk about something called harmonic eigenvectors, because the gut feeling when you see the normalized Laplacian is like, you see those square root of these floating around, and you're like, oh, this is terrible. This doesn't feel like combinatorics at all. Why would we even want to look at this? Other than the fact that you can do lots of cool stuff. And so is there a way to sort of think about things which don't involve square roots? And I'm going to try to convince you, or I probably will fail about convincing you, but at least sort of demonstrate something called the harmonic eigenvectors. And say, well, there is a way to look at something related to the normalized Laplacian which doesn't involve a square root. And so, all right, now, when we last met, we were talking about how we have this harmonic eigenvector. Well, okay, so that says d to the minus 1/2 L d to the minus 1/2, and I know x is itself an eigenvector, and so that says you multiply through here, and you have yourself a lambda x. All right, great. Well, this we'll call y, and we can move this d to the half over. You get L y is equal to lambda d to the 1/2 x. Well, that's not quite d to the minus 1/2 x, so we make it d to the minus 1/2. It's a great strategy in math. If it isn't what you want it to be, make it what you want it to be, and then say, let me just correct for my choices. And so to correct, multiply by d. So you have lambda dy. All right. Now, if we dig a little bit further, you might notice here that L, which is just the combinatorial Laplacian, that's the same as d minus a y. And so this is d times y minus a times y. All right, now we're almost there. So we've just essentially started with saying, what does the normalized Laplacian x equal lambda x translate into, assuming you replace x by this y, or y goes d to the minus 1/2 x. So for our last little bit of moving stuff around, we're just going to swap signs. So this lambda d sub y, this a sub y are going to swap places. And at that stage, we get the following. Namely, we have that a times y is equal to d times y minus lambda d times y. Or if you like, that's 1 minus lambda dy. All right, now how to think about this? Well, you might recall, so we'll do a quick little flashback. Let's talk about what does it mean to say ax equals lambda x. So where A was the adjacency matrix. And we said, well, there's a way to think about it in terms of the graph. And so how does that influence things? We sometimes call this the adjacency operator. And we're saying, well, what's the operation it's doing on the graph? And so the key was, he said, all right, look at the youth vertex. So we'll take this relationship, ax equals lambda x, at a vertex, and I'll say it's vertex u. So in other words, I'm taking ax at vertex u. I'm going to set that lambda x at vertex u. And what comes out? Well, on the right-hand side, that's no surprising. That's lambda x at vertex u. Okay. What does the ax at vertex u become? Do you remember? What does the adjacency do?
The sum of y sub, or x sub v for all neighbors of v.
That's right. So it's the sum over all v such that v is next to u. So in other words, it's the adjacencies of xv. So the idea is that for the adjacency matrix, what's happening with the neighbors? Okay. Well, now let's do the same thing. Okay. what do we have? All right, so we're at a vertex U. So this AY at vertex U, what's going to happen? I'm going to say, that's a mystery. We figured out what happens with AX at vertex U, but what would this AY at vertex U do? If only we could figure out. The same thing, yes, except instead of x's we have y's. Okay, so again, it says, look, hey, just add up your neighbors. All right, great, we can do that. Y sub v. And I should say here, underlying this is sort of an implicit assumption that says we're going to have a simple graph. You can have weighted graphs, and depending upon how slowly I go, which if history is any guide, I will go slowly. But if I don't go too slowly, we'll talk about some examples with weighted graphs. But you can modify this for weighted graphs. The only thing that happens is you add a weight function. So the weight of the edge from U to V. Okay, so what about the right-hand side? So what's going on there? So 1 minus lambda becomes, well, I'll give you the 1 minus lambda for free. Right, it's the degree of vertex U and YU. And so now we say, this is great. So that we can say, what's the difference between sort of a normalized Laplacian in terms of these harmonic eigenvectors and just the normal adjacency metrics in terms of normal vectors is that you've introduced this one term. So essentially you have this weighting term, the degree of U. And so how much can that really change things? Well, it changes things enough. And in some sense, you want to sort of take into consideration, and I'll go into more explicit about this later on, but it changes your perspective about how important is a vertex. Or, which vertices are important. Because the higher the degree is, well, you have to be a little bit more careful. So if all your vertices have roughly the same degree, but then one vertex has a much higher degree, well, that's you got to be a lot more delicate there. And there is a way, and this is not the right place to say it, but I'll say it now, and then I'll say it again when it is the right place to say it, which is that the way that the normalized Laplacian looks at graphs and graph structures is to say, we care about your connections. It's how you connect, and not about you yourself. And so, in other words, an edge-centric view of graphs versus a vertex-centric view of graphs. In a vertex-centric view of graphs, you say, what's important? Vertices. How many vertices do you have? That's what's important. In an edge-centric, what's important? How many edges? Well, what are edges? It's connections. How connected are you? That's what's important. So the punchline for the normalized Laplacian is it's much better at capturing connections. Now we will, as I said, this is just being vague right here, of having this degree term. But we will see in the future something where it really is very concrete. All right. Well, let's see. What are some fun things we can do here? What's a harmonic eigenvector that we get for free? it helps, it's an eigenvector that we're very familiar with. Yeah, let's look at the all ones. Okay, so the claim. So the all ones is a harmonic eigenvector. Well, what do we need to check? We just have to check, does it satisfy the relationship? Namely, if I sum over all the vertices which are adjacent to you of 1, does that equal, question, 1 minus lambda, times the degree of the vertex u times 1 for some choice of lambda? Well, I claim it does. What's the right choice of lambda? So if you sum, it's for lambda equals 0. Because what do you get? Well, if lambda equals 0, this is 1. And then you say the sum over your neighbors of 1 is your degree. You're like, great, beautiful, nice. Okay. Now, let's try something else on. Suppose we say that x is an eigenvector for the eigenvalue 0 for the adjacency matrix. Okay, so I'm claiming here x is an eigenvector of 0. All right, not that x is 0, because of course eigenvectors can't be 0. Then the punchline, then x is also what?
I feel like it has to be an eigenvector.
It's a harmonic eigenvector. That's true. For which eigenvalue?
For 1.
For 1. Yes. Because, what do we say? Well, to say that it's an eigenvector for 0 for A, says the sum of your neighbors is 0. Because we get sum of the neighbors is 0 times itself. So whichever vertex you're at, you sum your neighbors, you get 0. Well, now you say, okay, all right, come here and I sum my neighbors. I get 0. Well, okay, is there a choice for lambda which always guarantees 0? And the answer is 1. And so there is some connections between the eigenvectors of A and the harmonic eigenvectors of L, at least in this one special case. And moreover, you can show that the multiplicities are the same. Now, you can, roughly speaking, say the following. I'm not going to try to justify this, but we've talked about how the eigenvalues go between 0 and 2. And so here we have this eigenvalue of 1. And now we just said that the multiplicity, I can spell multiplicity, of 0 as an eigenvalue becomes the multiplicity you have for 1 as an eigenvalue. And I have to specify what matrices of A becomes the multiplicity of 1 as an eigenvalue for L. And between 0 and 1, what is this? Well, how many eigenvalues are there from 0 inclusive up to 1? Well, this is the number of positive eigenvalues of A. And similar, between 1 and up to 2, this is the number of negative eigenvalues of A. Sometimes people who study this like to refer to this as inertia. Okay. Well, let's inertia usually isn't between 1. You know, it's inertia of a matrix. You look at the number of positive, number of negative, number of 0 eigenvalues. All right, let's try a particular construction. So let's suppose we have the following. I'm going to build up a graph. So on the top of this, I have a graph H, which is regular of degree k. So in other words, here's a graph that's very nice. And because it's regular, it doesn't matter which matrix we look at. We can always scale or shift or do whatever we need. We can find the eigenvalues for one. We can find the eigenvalues for others. So life is fine. And now what we'll do is we'll have this graph. And we're going to connect it. We have these L vertices so that we're going to put in all possible edges that run between our graph H upstairs into these subsets of L vertices. Sometimes you might see this referred to as coning. But you're just connecting everything in H down into this set of vertices. And, well, finally we'll just have the rest. And we're putting no limitations on here, so there's some connections, but who knows? Okay, so this is our basic setup. Now the question is, can we understand eigenvalues of the whole graph, or at least some of them, if I know the eigenvalues of this original part? So in particular, let's suppose we can say the eigenvalues of our H, and we'll do it for the normalized Laplacian because that's our mindset right now. We have lambda 1 equals 0, and then we have the rest, lambda 2 up through lambda n. And now the question, what are some eigenvalues for the big graph? In other words, can we take these eigenvalues that we know of and get more eigenvalues? And I make no claim we'll get all the eigenvalues of the big graph, but certainly we want more. Who doesn't want more? Can we do anything? Should we try? We should try. We're getting close to the kind of thing I used to do when I was a graduate student, back when I was a young mathling, when the beard was still brown, no gray. Now, I guess I should pause for a second and say, since we know this graph is regular, how closely related are eigenvectors and harmonic eigenvectors? In H. So again, we can cover up the rest of the structure for just a moment. In H, how closely related are eigenvectors and harmonic eigenvectors?
Just up to 1 over k, or k.
No.
It's scaled.
Right, up to well, 1 over root k.
Okay.
But yeah, up to a scaling factor, they're the same. So that can be helpful for thinking about, this feels like things we've done before, because I hope it is. Because I do think it is. I get a feeling like it is. Any thoughts?
Well, you still have 0.
That's true, because 0 is a eigenvalue for this graph. It will also be an eigenvalue for that graph. All right, progress. We found one. All right, call it a day? No, we still have time.
I want K to be one of the eigenvalues.
Well, we can't say K is an eigenvalue, because remember we're
There's
It's
no
between 0 and 2.
has to be between 0 and 2, yes.
Based on how you're framing this, not based on any mathematics.
Sure.
Are the eigenvalues of H also eigenvalues of really tiny graph?
No.
Oh,
Would that it were so simple.
times something.
There is a transformation that happens. This is true. You speak the true truth. But the goal is to say, what is that transformation which happens? And can we figure it out?
Like, is every vertex in orange, like those L vertices connected to everyone in H?
Yes.
Oh, okay.
Every vertex in this grouping is connected to everything upstairs, and nothing in the rest is connected to H.
Okay.
H is still regular.
Very good. H is still regular. That will come into play. So what is the vertices that were part of H, they used to be regular of degree k, now they're regular of degree what? K plus L. All right, good. So K plus L will show up in our answer. I have the answer written down. I don't have the intermediate work. So this is good. We'll get to figure it out as we go through it. It'll be an adventure together.
You asked earlier, because H is regular, about the harmonic eigenvalues, or harmonic eigenvectors.
Mm-hmm.
Aren't they also regular eigenvectors?
What do you mean? Well, yes, they are, because they differ by a scale.
Yeah.
So
Are the L vertices like, are there any edges there or?
there could be.
Okay, there could be.
I'm not making any assumption about that.
Mhm.
So there could be edges among these L. If you want, we'll throw some in. If that helps, it makes it less complicated or more complicated, I don't know.
No, I'm just making sure that I understand the setting here.
Oh yeah, absolutely. As the screen comes in and out, don't worry, we have plenty of time to meditate on this. And if you're watching the video later on, you can just watch it at double speed and wait, okay, when does he start writing again? That's when an idea will pop in. Does the question make sense?
Yeah.
And if that's a good sign, if the question makes sense, what have we done in the past?
Start looking at
Hmm?
Each of the sort of components with constants.
yeah. There's
Well, there's just one component.
It is one component. I was like, components.
Oh, I'm sorry.
Heavy.
Okay, there are multiple components with quotation marks. Sure. One could say that in some sense there's sort of three important pieces of the graph, but
Like when we have bipartite, but that's not. Is what I was imagining.
Sorry, I didn't realize what I was saying earlier. I think the eigenvectors for L, I think the harmonic eigenvectors are eigenvectors for A, for H.
that is true. Yes. It turns out if your graph is regular, then your eigenvectors are the same for basically all the main matrices we've talked about. So for adjacency, Laplacian, signless Laplacian, normalized Laplacian, you can use the same set of eigenvectors.
Oh, very cool.
And that's just because the matrices themselves are related in very simple ways. Essentially either scaling or shifting or both.
Yeah, I guess if it's regular, it's like delete D. Like delete the diagonal of the Laplacian.
Right.
Yeah.
So when you see people make assumptions, assuming the graph is regular, you know they're doing cheat mode. You know, it's like they're playing a video game and be like, okay, I have all the weapons automatically loaded before I even start.
So you asked what we usually do in cases like this.
Yeah.
We usually take eigenvectors for H and extend them to eigenvectors of the entire thing, right?
Cool, let's do that.
That is
Right?
the goal, yes.
So let's see. All right. So what should we call now? Let's do harmonic. Just sounds cool, you know. And we've invested time today to keep saying it. Okay, so let's suppose we have a harmonic eigenvector for H and for eigenvalue, let's say lambda. We can even say lambda I. Now, when I say lambda I, one of these I'm going to ignore. Which lambda should we ignore?
0.
Yeah. 0 is kind of weird. You got to like move that aside, put it off. We'll come back and talk about it later. Okay, so we have one of those. So what does it look like? Well, I didn't say it out loud, but since I gave m eigenvalues for H, I'm going to assume that there's m vertices. So I'll call it y1 down to y sub m. Okay, so there's the harmonic eigenvector. And so now we say, well, maybe this works for the whole graph. So let's try. What are we going to call it? Well, we'll call it y1 down to ym, and the rest of it will be 0. And see if it works. Now, I don't claim that it's automatically an eigenvector for lambda I we'll say for some eigenvalue. And so that's our goal, to try to figure out, does it work? And if it does, what's the eigenvalue that does it? Okay, so let's start by saying we know it's a harmonic eigenvector for H. What does that tell us? We go back to our definitions. And I can very conveniently have it written down in front of me, off screen, but I'm just copying from the paper here. It says if we sum over all the vertices in H, which are next to U, of y sub v, that this is equal to 1 minus lambda. Now, I'm going to use the fact that we know what the degree is. The degree is k times y sub u. Okay. Now, we come to a couple of let's do it over here. So what's going to happen? Well, we have 3 cases to consider. Where should we begin? Let's start down at the bottom. We'll call this case A. So in case A, well, we have the sum over all the vertices adjacent to U, and we'll call G our giant graph, of y sub v. And the question is, does this equal our 1 minus mu, so we'll call mu a temporary name for it, times the degree of u, well, we don't know what the degree is, times y sub u. Well, is this always going to be true, and if so, why? If you're down here, where are you at in terms of your eigenvector? Yeah, this part should be 0. So the right-hand side is 0. What about the left-hand side? It's also 0, because the only thing that you're connecting to are either in the rest of it or maybe up to L, but all of those things are 0. Okay, so great. So we're definitely going to be okay down on that level. Moving our way up. And of course, this will date me when I say, you know, there's always the exciting news that in our elevator in Carver Hall, it used to be that one of the elevators would say, they used to both say G for ground floor, but one of them now says B for basement, because they updated it. They've replaced it. I don't know if you've noticed this, but it's, you know, exciting times that we're living in. Okay, so for B, now things get slightly more interesting. Again, we don't know the degree. It could be all over the place because it depends on how many edges it connects to down in the rest or in between. But what can we say? What should the right-hand side be? If we're here in our middle, should be 0, right? Because we assign things to be 0. All right.
If you're adjacent to anything else, you're adjacent to all y1
Very good. Now we're doing something. Certainly, we don't care about the adjacencies not in H, but if you're in the middle layer, you're adjacent to everything in H. Yes. So now we pause and say, we'll do it here in the corner, for I equals 2 up to m, what can we say about the sum of our yi's? And, all right, you go ahead and say that. And why is that? There is a reason why. We channel our, what have we been learning? We know things. Things are good to know.
Is it because it's regular?
It's like I wanted to.
It's definitely,
I want to say they're perpendicular to like
Right, it's perpendicular to the eigenvector for the first eigenvalue, which came from
Regularity, but I can't remember why.
from the all ones, because we have the same set of eigenvectors. Now, regularity is important here, because you might say, wait, when are harmonic eigenvectors regular in general? It's not as easy, because harmonic eigenvectors, which I was going to point to the screen as if there was one on the screen, but harmonic eigenvectors, because they have this extra factor of the d's floating around, it's not as easy as saying, oh, they're still perpendicular in our traditional sense. You have to weight things appropriately. But when it's regular, it's like, doesn't matter. So the scaling factor just goes out. And so because we know that the eigenvector for 0 is all ones, and we're regular, we say life is good. All our sums are 0. So yes, that's why we're cheating here. That's okay. We're honest with people. We tell people our assumptions and why we make them. All right, so the punchline here is the only things which are non-zero are up here, but because we're adding up all of them, we'll get 0 on the left-hand side. Okay, so far we've cleared 2 levels. That means 1 level left to clear, and life is good. All right, so we're upstairs. So we have our sum for all our vertices, v next to u of yv, and this is supposed to equal, of course it equals something, 1 minus mu, and our degree of u, and y sub u. But now we can start being a little bit more, things actually go on. So the degree upstairs on our top level, we actually know that. What is our degree upstairs? K plus L. And really, you say, look, vertices in G, but the only times that we get anything that's non-zero is when we're in H. And now we say, well, isn't that interesting? Those seem to match. And they do. So it says, okay, so this should also be equal to our 1 minus lambda times k times yu. And now we come to our moment and say, well, what needs to be true? What we need are that these pieces need to line up. They need to agree. Now, remember, k, l, and lambda are all things we know. So the real question is, what's mu? What's our new eigenvalue? So now we just have to say, all right, 1 minus mu times k plus L has to equal 1 minus lambda times k, and solve for mu, and we'll be done. Well, how hard could that be? And 1 minus mu, I can just divide by k plus L, 1 minus lambda times k over k plus L, and then we can swap sides. So we could say mu is 1 minus lambda k over k plus L. But maybe we can clean that up a little bit. Common denominator is k plus L. So we get k plus L minus, and we'll distribute through. That'd be minus k and plus k lambda over k plus L. And yeah, the k's and the minus k's cancel. And so we're left with, well, let's see, how should we write this? So L plus k lambda. And I'll just reverse the order so it looks pretty downstairs, L plus k. Now, of course, if you were like one of our calculus students, you might be tempted to say, hey, you know what? I see I can cancel an AL plus K upstairs and downstairs. No, that's not how it works. No points for you, but okay. But you know, it makes you want to say that. And so, okay. Now, as a consequence of this, one thing that you can now do is you can actually work out joins of regular graphs. So if you start with two graphs which are regular, so you have h1 regular of degree something, I don't know, I'll call it k, and h2 regular, and I hate to use L here, but I'll use it. And you look at the join. This does not have to be a regular graph for the normalized Laplacian. It doesn't have to be bipartite. And so you might say, well, can you work out what the eigenvalues are? And the answer is yes, because essentially what you're doing is here, you're just joining all of H into this side. And so you've now figured out, I know how to join. I take everything in H1 and I join it to everything in H2. Then what you really have is just your two layers. You have your H1 and your H2. Then you can repeat it for the other side, and then you say, well, but that doesn't capture everything. We're short. By how much?
2.
We're short 2 eigenvalues. One of them is a freebie, and the other one then becomes a freebie. Which one's a freebie? 0, because 0 is always a freebie. And how do we get the other one? Now that we know, if you know all but one eigenvalue, how can you get the last one? You can go to the trace, because the sum of the eigenvalues is the trace. The trace of the normalized Laplacian, let's assume no isolated vertices, because in joins there aren't isolated vertices. The trace is number of vertices, yeah, because it's 1 on the diagonal. So it's the number of vertices. So now we can do joins. And on that note, we should start winding down. But I see a question.
Why does case B, I don't understand why case B works like case A. I get that the middle
Right.
one is going to end up being 0 because of the way we constructed our eigenvector, but it's connected to things in H that are not necessarily, is it
Right.
going to work out because of the...
Well, so this is where we heavily lean into, we're putting in all possible edges. And so why does it work is if you pick a vertex here, it's not that you're adjacent to some things upstairs, you're adjacent to everything. And so when you look at the sum of the neighbors, you say, well, the sum of the neighbors is in the sum of all the entries. And so what we're relying on is there's a nice thing that says if you move away from the trivial eigenvalue, eigenvector, then everything else has a nice relationship to that when you're regular, which means you're perpendicular. So think about what perpendicular relationship in terms of the sums. So normally we think of like, you take the dot product of the two vectors is 0. Well, a dot product is a sum of multiplying the entries. And so in particular, this is really the dot product of the all ones vector with this other eigenvector. And so there's this sort of hidden dot product we're using, being 0. So, see, and look, they let me graduate doing this kind of stuff. So you too can get a degree in mathematics. Yes?
In case C, I feel like I'm forgetting something. Do we know that YU is not 0, or how do we know that?
Well, we don't make any claim that YU is not 0, but we make a claim that some YU is not 0. So this has to be true at every vertex.
But there exists some vertex where YU is not 0, and you use
Right.
that one.
Yeah.
And divide it.
Right.
Okay.
So I mean that's a good question because it's like, Steve, why are you ignoring this? But yes, thank you for pointing that out. Because you're right, because when YU is 0, it's trivially true. But somewhere out there, there has to be a non-zero entry, because otherwise it couldn't have been an eigenvector to begin with. Because harmonic eigenvectors can't create or destroy 0 entries. It just scales entries. So, all right. Well, that's it for today. We'll pick up next time with equitable partitions.